Hi guys, this is Merlin. I'm just gonna talk about it today. I'm just gonna keep like explaining those kind of deletion and insertion stuff, because and the deletion parts I'm always I'm implementing deletion part and still don't know what's going on here, and so I think it's very good to trying to explain the some kind of the keywords or some kind of the hard part of algorithm data structure, because I think this is important. So the B-tree is, I talk about B-tree, what is record key and what is index file and those kind of thing. And now I'm just gonna try to talk about the insertion part or so. So if you're trying to so the B-tree, I think like the core thing is making the depth of the tree height into short enough compared to binary tree. So how do we do it? How do we make that happen? So that is gonna making this kind of putting a lot of keys on the one node. So example, like binary tree, they only have one node, so one key in the one node. But the B tree isn't that. B tree can have multiple how to say it, multiple key in the one node. So in example, if I'm trying to delete, like example 11, so 17 is bigger than 11, so 11 go left, and 11 is bigger than 10, so it got right. So 11 is gonna be put in this part. Now you can see we only traverse 1 and 2 and 3 now. So that's kind of very efficient if it requires a really big data. Okay, you insert 11, but that's pretty nice. But let's try to do a search. For example, your target key is 18. You go right because 18 is bigger than 17, and you go left of the 20 because 18 is smaller than 20. So you find out that 18 is here. But that's pretty good. But there's a common issue that we face. The binary tree, the B tree, isn't really efficient. But what if there are like multiple query search? Example, you want to search the 18 to 30. But since B-tree only have a search optimization in the one key, it's kind of really bad for the range key, because if it's not range, it's gonna be log it was like n, it was like, yeah, it was like t and n. I think it was like log n plus the k equals to be number of the range keys, and then I think the t is gonna be minimum degree of, or the max size of node can have. So since this k plus k divided by t requires more time complexity, I think there's already optimization for it. I think it was like b plus 3 or bpa, those kind of thing. But that's, we don't really have to know about this. But so we go one key here. So but range key, we have to search on the search part of here, this part. And also there's some kind of double linked list on the B tree, but what I believe that's kind of like B plus 3. I think B plus 3 is using double linked list of the B tree, and that enables traverse back into the parent of it. So now as you can see, the insertion is pretty nice, but insertion is getting hard. But if what you insert create makes the node overflows. For example, you put 31 here, and let's say maximum keys in this part is 3, but it already oversees 3, and you have to make the primary key and goes to the parent. So the primary key is t minus 1, and the t minus 1 is now is 22. We did in here this B3 t is 2, so t is 2, t minus 1 is 1, so their one index of in this node is 22. 22 has to go into this part. And next, you already went to 22 in this part, and now the next part is So next part is 21 and 31, 30 and 20, 31. But we already, this keys, the length of the keys is 3. It's not over the 3, so we just keep it happen. So the 22, we're gonna point this part. And 21, this is gonna point 21, and 22 is gonna point this part. So to make it clean, on this part, this is gonna be separated like this. So the key is gonna be go here, the pointer is gonna go here, pointer will point the 21 here. So this is really hard part insertion of this. But what if there's like more, if you what you create, example you append the new primary key into parent, right? But what if this key is already full enough, like the one we handle with the child? So this has to go to with the parent key. So this propagation makes more time complexity of it. And next, the deletion part is very simple. Deletion part is simple when if you try to delete, the target key is leave. And also, this what you're trying to delete doesn't cause underflows. If you're trying to delete 6, there's no issue of it. But if you're trying to delete 5 and 7, there's gonna be issue because there's no key in this node, so there's gonna be unbalanced. But deleting 6 is easy. And deleting 10 might be also easy because you can borrow 7 from the child and you can put 7 here, and there's only 5 and 7 and 12 here. So that's really kind of good part. But what if you delete the 5 here? You cannot borrow other things because there's only 12 or 7 in this part. So what you have to do is borrow from the 17 and you merge it with the child, and you make a new tree of it, subtree. I think that's really hard part of the bit tree deletion. I think this is the most difficult part of the bit tree. I don't know what's gonna happen, so I'm still implementing with the TypeScript. If you look at here, my TypeScript code is already here and it's already open source, so you can see it. But my code is still there, so I don't know what's gonna happen. So this is it. Have a nice day. See you next time. Bye bye.